have it. Yeah, I'll give you one more minute. Okay, so what do everyone get for this A?
1.29.
1.29?
I got 1.68.
And then B? Or C? We'll figure it out. 1.68. Let's check this.
1.5.
I got 2.38.
2.38.
Yeah, there we go.
All right, so there's a lot of variations here. Let's go ahead and do this. So first of all, for this angle here, what side is this A?
Adjacent.
Yeah, it's the one that's not the hypotenuse that's next to the angle, so it's adjacent. And this side is the opposite, right? So if I know the opposite side and I want to get the adjacent side, which trigonometric function involves both of those?
Tangent.
So I know that tangent of 40 degrees is just one way to do this. You could do many other ways. But I know that the tangent of 40 degrees would be the opposite to that angle, which was the 2 meter side, over the adjacent, which was the A. So 2 meters over A. Now if I want to figure out what A is, I got to solve for it. So first thing I'm going to do is I'm going to multiply both sides by A. This doesn't get me what A is yet, but if I divide both sides by that tangent of 40 degrees, I will get A by itself. And so I'd get that A would be equal to 2 meters over tangent of 40 degrees. Okay? So if I plug that in, what do I get?
2.38.
2.38 meters roughly, approximately. Okay, good. Now there's many ways you could get C. You could use a Pythagorean theorem. You could use, any other trigonometric function you want, cosine or sine. You could write this as 50 degrees, since we know that the total number of angles in a triangle has to be 180, and you could do similar stuff for this angle if you wanted to. So there's a whole bunch of ways to get C. I'm just going to do the Pythagorean theorem and say that C is going to be equal to square root of plus 2 meters squared. And I could just evaluate these numbers and remember the unit's going to be meter. And what would you get? Three.
0.11.
Because it's 2.38 squared, it's gonna be 5.6 basically, and so what's a 9.6,
Okay. That's some good arguments.
3.11.
What's that?
3.11.
Sounds about right. Okay, that makes sense how we did that? All right, one more trig example. This one comes up fairly often and is important. What's that?
Oh, nothing.
Okay.
My calculator's giving me the wrong answer.
Go to the gym, go to the drill.
That's usually a user error I found with calculators. And probably the easiest mistake to make is order of operations.
No, I think it's in radians versus degrees,
Oh yeah, that'll be a bad.
and I don't know how to
mistake, too.
change it.
Oh.
It's just on my phone.
I see. Yeah, there's usually a mode somewhere. All right. Let me see if I can do one other example. Let's say that this is 1 meter and that this is 1.5 meters, okay? Could you get that angle? All right, how do we do that? Bunch of ways. There's a bunch of ways to do this, but if I know two side lengths on a triangle and I want to get an angle, I'll look for the trig function that has those two side lengths in its definition. So in this case, I know that tangent of theta is opposite over adjacent. Which one's the opposite side?
1.
1 over 1.5, and I just left off the meters because they'll cancel in the ratio. Okay. So now what do I do if I want to get that angle? That's right. You take the inverse or arctangent, and arctangent of tangent of theta is just theta. Okay? So if I take the arctangent or inverse tangent of both sides of this, I'll be left with theta on this side and arctangent of this on the other side. So I get theta is going to be equal to arctangent of 1 over 1.5. And you can evaluate that in your calculator, right? Of course, you'll get it to me in radians. Because you know, if you're in radian mode, you'll get an angle back in radians. But if anyone in degree mode, can you tell me what that is?
33.69.
33.69. Okay, about 7 degrees. Okay, 33.7. Everyone get that? Very good. All right. So that's trigonometry in quickly. It really isn't that bad, but you do need practice at it. There's no real way to get comfortable with something unless you practice it. So. Luckily, the next topic we'll be covering is vectors, and that gives us much more trigonometry practice. And vectors are going to be used throughout the rest of this class quite often. So, and the lab. So vectors. Okay, say I'm looking at a map and I say that I'm at Hays, Kansas. And I'm trying to give instructions to somebody to go to Kansas City, and I told them to travel 302 miles. Would that tell them how to get to Kansas City? No.
They just happen to be pointing east on I-70, maybe.
See, the thing about there's distance and then there's also position. And if I wanted to really define how to get to Kansas City, I have to tell them both the direction to go and the distance. So that's an example. So, but the position of something has two things to it. It has both a distance and a direction. Has a distance and a direction. And this is an example of a vector. Okay? So an example a vector. So for instance, actually I'll write the position of something as a vector R. To distinguish it from quantities that are not vectors, I write a little arrow like this over it. That's just an example of a vector. A vector is anything that has a size and a direction. A vector has size and direction, or magnitude. And direction. So many other physical quantities will be described in using vectors as well. So for instance, if I'm saying that I'm traveling at 100 miles an hour, does that tell you exactly what my velocity is? See again, it tells you how fast you're going. It doesn't tell you where you're going to end up at all, because I need to define a direction. So velocity, which is another example of a vector. There's a magnitude of the velocity, that'd be the 100 meters a second, 100 miles per hour. And then there's a direction associated too with that much. Forces would be another thing that has a vector. I can exert we haven't talked at all about forces, but everyone I think has some sense that a force that I exert here, I might be exerting the same size of force as the force I exert here, but those are two different forces, right? One's in that direction, one's in that direction. So forces will also have a size and a direction, and so they'll also be vectors. And anything using these positions, velocities, forces will often also have will often also be vectors. And so vectors will come up quite regularly in physics. We symbolize a vector, or we can draw a vector, writing a little arrow. Anyone look at any of the weather maps and stuff like that? If you look at those, a lot of times they have like a layer that you can look at where they tell like the relative wind direction and stuff. They'll so at every point where they're measuring the wind, they have a little arrow. So that'd be the velocity vector for that wind at that point. There's many other places where the vectors come up. But this will be how I'll draw a vector. The length of this arrow, I'll call the size of the vector. So length of arrow corresponds to the size of the vector. And the direction of the arrow is the direction of the vector. A lot of times it becomes very, very convenient to introduce a coordinate system to describe vectors. So for instance, when we're talking about position on Earth, there's a coordinate system kind of in place. People knew this without really thinking about it, I think, that there's east, north, west, and south. That's kind of the coordinate system, right? That'll tell me my direction of the vector. That's all that a coordinate system is it's going to tell you direction of the vector and, as well as the size. But it'll help tell those things. The coordinate system, vectors are real physical quantities in the sense that they're real positions, really velocities, really forces. But the coordinate system I use to describe the vector, that can be, in any orientation I want. It's kind of, people have defined the coordinate system. They're not the real physical quantities. So you could have more than one coordinate system to describe a vector. In any given problem, you're going to want one coordinate system and be consistent with it. So the typical coordinate system that we'll use, hopefully this is pretty familiar. Cartesian coordinate system. We're going to mostly deal with vectors just in 2 dimensions. In this class, if you take physics 2, you will run into vectors in 3 dimensions. XY coordinate system, if I draw a vector A here, by drawing a coordinate system, I can see how much A goes over in one direction and how much A goes over in another direction. So if I call this, I'm going to label this as an A sub Y and this is an A sub X. These are called components of a vector.
Basically, the distance you move to the right and the distance you
Yeah.
move forward.
Yeah, A sub X is the part of the vector in the X direction. A sub Y is the part of the vector in the Y direction. And these are called components. If I have my coordinate system defined and I know these components, I pretty much know the vector. I do know the vector, everything there is to know about the vector. All right. Anyway, I'm going to have to let you go now. And Friday will be all about vectors. Remember, there's a lab tomorrow. Yes.
Yeah, what do
You're going to need a lab notebook, a brown lab notebook that you can get from the bookstore. Okay?